Good morning, guys and girls. Hope everybody's doing well. Hitting the home stretch here in chapter 12. This week, I want to walk you through characteristics of phase diagrams on Monday. On Tuesday, want to talk to you about heating curves. Wednesday is going to be a review day, and I should send the test your way. Thursday will be time for you guys to work on the exam. And then Friday, I'm going to go ahead and start easing into the next chapter. So today's theme is all about what you see right here, right? Phase diagrams. So big themes throughout the entire chapter have been that solids have certain properties, liquids have certain properties. From previous chapters, we knew gases had certain properties. So we learned about each of them individually. And then what we did was we transitioned into morphing from one phase to another. And we got into phase changes such as melting and boiling and freezing. And the latest thing that we've done is when we were talking about boiling on Friday, it seemed to become apparent that the pressure exerted on the substance seemingly has an effect on what phase it lives in, that it's not solely based on the temperature that the substance experiences. And we said that at lower pressures, you can see things boil at a lower temperature because you overcome the intermolecular forces and the pressure, and it doesn't need as much heat to do so. And then we talked about our pressure cookers, all right, our Instapots, and they functioned on the exact opposite. They increased the pressure inside the container. And with that increased pressure, it required more heat for substances to boil. And then once they do, that steam and that liquid that's in there is now at a higher temperature, so it cooked things faster. So there is absolutely a link between temperatures and pressures. Phase diagrams try to, in a pictorial way, show you those links. All right, so on this first slide here, I'm going to show you what a phase diagram is, how they're all similar, show you some of the key points, and then we're going to break them down more individually. All right, so by definition, a phase diagram is a graph of the pressure versus the temperature, and it will tell you what phase the substance will exist. So all phase diagrams have the pressure over here on the y-axis, temperature over here on the x-axis. Units on those can vary. Right? I've seen phase diagrams in atmospheres. I've seen them in kPAs. I've seen temperature in Celsius. I've seen temperature in Kelvin. It just matters that you have pressure on the y-axis and temperature on the x-axis. So all phase diagrams, right, have those things in common. Then what they do is they show you where certain phases live. Now, they're not all identical, but for the most part, you'll see some similarities. If I jump out here, most substances will experience the solid phase out here in the top left. And so the solid tends to live in the upper left because low temperatures tend to make things freeze and high pressures tend to make things become solids. The bottom right phase tends to be your gas phase. High temperatures means there's a lot of energy present to break particles apart and overcome atmospheric pressure. So there's a high likelihood that at these high temperatures, you will be a gas. And then in the middle somewhere, and this is the thing that changes quite a bit depending on the substance, you will have a liquid. All right, somewhere in between those two. And how big that liquid phase is can vary. Same with the solid, same with the gas. All right. And where it occurs on the pressure scale can vary as well. All right. But you've got solids generally on the left, liquids in the middle, and gases on the bottom right. Another characteristic of phase diagrams is they all have this thing right here called the triple point. All right, and if you look over here, the triple point by definition is the temperature and pressure where a solid, liquid, and gas can coexist at equilibrium. All right, so that's kind of a unique idea. Right, we have seen phase changes that occur in two directions, right? Melting and freezing go hand in hand. I can see ice and water coexist. I've seen steam and water coexist when I watch a boiling pot. But this point here, the triple point, is really unique because at this point here, these conditions, you would see ice, you would see water, and you would see steam all happily living together at the same time. You would also see all the different phase changes that occur all at that one point. So I would see a substance freezing and boiling at the same time. I would see a substance subliming and melting all at the same time. So it's a really crazy set of circumstances where the molecules are just existing in different arrangements at that point. And the conditions for water are pretty difficult to obtain. The temperature is not bad. The temperature is right around 0 degrees Celsius, and I have a picture that shows it to you more specifically. Right, so it's right near the freezing point, but the pressure at the triple point is really low. I think it's like 0.01 atmospheres, give or take. Right, and that means we're almost experiencing a vacuum. Right, so some substances, triple points, are much easier to get to, but water's is not as easy to get to, which is why you don't have much experience with it. But the moral of the story here is that the triple point is where all three phases coexist, and it's where the three lines meet. Right? So right here you have a line that separates your solid and your liquid. Here you have a line that separates your liquid and your gas. And here you have a line that separates your solid and your gas. Where those three lines intersect, that vertice is the triple point of any substance. All right, so that's a unique characteristic about the graphs. All right, another one is there's a thing called the critical point. And the critical point is this guy here. So it lives way up high on the graph. And notice, it's only separating two phases, the liquid phase and the gaseous phase. All right, so it's not like the triple point where the solid is in here. The critical point's a bit different. All right, the critical point is the combination of what they call the critical temperature and the critical pressure. So if we traced over to our axes, down to the X and over to the Y, whatever this numeric value was for the temp and whatever this numeric value was for the pressure, that would be known as our critical point. All right. And definitionally, it's kind of simplistic. The critical point is the substance's critical pressure and temperature, that one individual point. So let's dive into that a little bit deeper. What's the critical temp? So the critical temperature is the last temperature that it is possible for a substance to remain a liquid, or you could think of it the other way, that if I exceed the critical temperature, I have to be a gas. So for water, that temperature is 373.99 degrees Celsius. So if you look down here on the x-axis, you can see that value. right down here. There we go. All right, you can see that value. And this temperature right here is so high that if I put that amount of heat on my substance, it does not matter what we do to it. It has to separate into separate gas particles that would escape. And you're going to say, well, wait a second, that's a really high temperature. Why isn't it a gas anyway? Well, like we were talking about the other day, I can make a substance stay a liquid longer by pushing down on it with atmospheric pressure, just like we were able to make our water in our Instapot hotter. If we put enough pressure on the water, we can keep these particles from escaping. All right, so that value right there is known as the critical pressure. All right, for water, it's about 218 atmospheres. So if I put that much pressure on the surface of the water, it can force a really, really hot water sample to stay liquid. But the moment I get past that 373, these guys will all possess enough energy to overcome any amount of pressure, right? No matter what. I could put 1,000 atmospheres of pressure down and 374 degrees Celsius. It will not matter. The substance is going to vaporize. So if we looked at this graph here, think of the critical point as going directly north, and everything from here, here's the last spot you could be a liquid, and then right here at this asymptote, you would be a gas exclusively. The moment I click one past this, everything is a gas. All right, so that's known as the critical temperature. All right, you heat it up to that point, it is forced to be a gas. Right, and like I said, the last pressure that you're able to make it be a liquid at is known as the critical pressure. So this 217.75 for water, all right, is the last pressure that I can force it to be a liquid. If I go above that temperature, doesn't matter what the pressure is. And then for everything else, you can just look at the graph and decide what phase you're going to be in. All right, so you've got your critical point, which is the combination of the two, the critical temp, which is the hottest temp that will make it be a gas, and the critical pressure, which is how much force you have to push on the liquid to make it be a liquid at that last temperature. All right, so then obviously, since we're looking at solids, liquids, and gases, phase diagrams, phase changes are a factor. All right, so another way that we could label that graph, and I do it on separate slides just because I didn't want to clutter up what you were seeing, is our phase changes, right? So if we look here, and the solid tends to be on the top left and liquid in the middle, if we are on that line in between them, we are either melting, because we're either going from a liquid to a solid, or we are freezing. We're going from a solid to a liquid. All right. If we are in between this phase of liquid and this phase of gas, that means we're undergoing either vaporization or condensation, right? So if we are anywhere along this line, we're either vaporizing or condensing. And why both? Because it just depends on where you start. If I was up here and I'm cooling the substance, the moment I touch that line, I'm going to start condensing. But if I were here and I heated the substance when I hit this line, I would be vaporizing it because I was taking the liquid and it is starting to turn into the gas. But on the line, both phases are present. And then down here is your sublimation deposition line, right? The interaction between the solid and the gas. All right, so kind of your rules of looking at your phase diagram. If you are not touching a line in between phases, the substance is in one phase only. So if I gave you a set of data points and it put me right there where the X is, you would just be a solid. Right? If I gave you a set of data points and it put you right where I put that little square, you would just be a liquid. But if I gave you a set of data points and it dropped me right here, touching this line, that means two phases are present. I would have solid and liquid, and they would be participating in a phase change. And if all I did was give you that one set of conditions, you wouldn't know. You would say I'm melting or freezing. But if I told you where they started and where they went to, you could be more specific is it melting or is it freezing for that. All right, so these are other common characteristics of your phase diagrams. I wanted to show you some slight differences that you'll see between some phase diagrams. So if we jump back over here, here's a side-by-side of carbon dioxide with some water. Now notice, both of them have the solid living top left. Both of them have gas bottom right. Both have liquid in the middle. They both possess critical points. They both possess triple points. Now, what those values are drastically different, right? Notice my triple point for carbon dioxide is occurring at negative 56 degrees Celsius in 5 atmospheres, whereas water, it's 0.0098 degrees Celsius and 0.006 pressure. Drastically different where those occur. So that's a big difference between them, as is the critical point. Critical point for the carbon dioxide, 31 and 72. Critical point for water, 374 and 218, like we talked about. And then visually, you'll see that you have a big difference in the liquid phase. Water tends to exist as a liquid much, much more than carbon dioxide does. So the liquid portion of the phase diagram for carbon dioxide is very tiny. The liquid phase for water tends to be a bit bigger. And those will all vary in substances predominantly based on their intermolecular forces, how strongly the connections are between them. The stronger the connections, the bigger the solid phase tends to be. Right? The weaker the connections, the bigger the gas phase tends to be. And some of them are so complex that you would see even more than 3 phases, right? There are certain substances like carbon. You know, carbon has multiple forms, graphite, diamond, all right, that you have 4 seemingly phases. So we have 2 solid phases. In carbon, we have a liquid and a gas. And look how big of a chunk of your phase diagram is solid phases, right? From 0 to 4,000 and up to times 10 to the 11th in pressure. Carbon almost always exists as a solid. These temperatures, 4,000 to 6,000 Kelvin, right? And these pressures that you have to get to for that to occur, right? Times 10 to the 7th is tens of millions, all right, are almost unattainable for us. So we do not see liquid carbon. We do not see gaseous carbon very much, but we know we could. All right, and that's because carbon's a network solid and it has super strong connections. All right, sulfur is another one that has 4 phases. You've got the gas, you've got the liquid, and you've got 2 solid phases. All right, rhombic and monoclinic. All right, and just realize this is one crystal just changing to another crystal because of the pressure. All right, so we have the graphite crystal lattice, which has one set of arrangements. And when we put enough pressure on it, we can change that arrangement into a different arrangement, diamond, and those characteristics will be different. The same is true between rhombic and monoclinic. We put pressure on it, and then all of a sudden we make the substance undergo a solid to solid phase change, which we don't get into much, but I just wanted you to see that a phase diagram doesn't have to have 3. That solid to solid phase change is just called polymorphism, in case you run across that term. So what do the questions tend to look like when we do these? Well, they take kind of one of three forms. And here are the three styles of questions you'll see about phase diagrams. Style one, what phase are you in at a certain set of conditions? So a question like that could be like this. I could say to you, hey, at 200 Kelvin, or sorry, degrees Celsius, and 4 atmospheres, what phase are you in? And what you guys would do is find those conditions on the axis. So the temperature scaling here, there's 100, there's roughly 400. So let's say 200 puts me in here. And 4 atmospheres, here's 1, here's 217. So 4 is basically here. We trace up to the intersection of those points. So we'd go there, we'd go there. And then where those points intersect, we're looking at this right here. Right? Where am I at? I'm not touching a line. Right? I am solely a gas. I could say something like, hey, at 200 atmospheres and 2 degrees Celsius, what are you in? And you'd say, okay, 2 degrees Celsius, right? We're pretty much right down here. 200 atmospheres, we're way up here. So that means we're talking about this point, right? 2 degrees and 200, trace over. So we're talking, sorry, about that point right there. All right, where am I at? In water, there's my gas, there's my liquid, there's my solid. You would say you're a liquid. And then don't forget, one more in the green. If I said, hey, you are at 100 atmospheres and 340, and it lands me right here, if your points draw and land you right on a line, you'd have to say, okay, it's liquid on this side, it's gas on this side. Hey, I am undergoing a phase change. I am either vaporizing or condensing. And you would say, I'm undergoing the phase change of one of those two. And both would be fine. All right. So that's question style number one. Question style number two. What happens if I go from one set of conditions to another? All right. So this is all about tracing where you are on the phase diagram. So I could say, what if we are at 400 degrees Celsius and 10 atmospheres, and I cool that to 100 degrees Celsius, but stay at the 10 atmospheres. All right, I give you two sets of conditions. All right, so sets of condition A, you would say, okay, 410 atmospheres, trace up. I'm right here. You know, at those conditions, I'm a gas. Then you jump into sets of conditions B, 100 degrees Celsius, 10 atmospheres. I'm here. That means I'm a liquid. So you had to go from here to here. You went through a line. That means you underwent a phase change, right? And you know what phase you were. I was a gas, and now I'm a liquid, right? So you would specifically say, I would see condensation because I'm going from the gas to a liquid. All right, so just figure out where you start, figure out where you're going to. If it all occurs within the same portion of the graph, you would just say, I remain a liquid. If, however, though, it pushes you through a line, you'd have to state the phase change that happens. And then the last question is, how can you make something occur by manipulating the conditions? I could say that I have a substance and I know that currently it's a liquid. Okay, so I can say, hey, I'm a liquid, and I'm saying, hey, I am a liquid at 50 atmospheres and say 100 degrees Celsius. I can say, what do you need to do to freeze it? Right? So I can say, well, I want you to freeze this substance. What do you have to do? Right? If you're at that 50 atmospheres of pressure, and you have to think and say, okay, so I'm stuck at the 50, but I need to make it so that I go all the way across that line and then drop down into here and figure it out. You would want to say, hey, I would need to cool the substance to some negative Celsius. I would have to make it so that I push through that freezing line, and you would tell me the new conditions. You'd be at 50 atmospheres and you need to go to negative 20 degrees Celsius. And the questions are pretty straightforward. I mean, that's all there pretty much is those three styles. All right, so just wanted you guys to see a little bit like that. So homework coming your way in the parent square is going to be page 382. Right, numbers 5 to 8. All right, and that has some questions about boiling and boiling points from Friday, and it has some stuff about phase diagrams on that, and I'll give you some guidance on that in the parent square message that I sent out. Hope everybody is doing well. Tomorrow, I'll probably do one more pre-recorded that you guys can watch it. As always, I'll jump on real quick from 1 to 2 if there's any questions on the topic of the day. And then Wednesday, let's plan on an actual live Google Meet from 1 to 2. I'll start posting some questions, practice questions that you'd see for your test, and we can get all the questions out of your system so everybody is ready to go for the test when the time comes. Look forward to hearing from you guys soon. Thanks.